Greetings, everyone. This is Jeff Wilkerson, Professor of Physics at Luther College, bringing you the next in our series of what to look for in the night sky. We're talking about the week of August 7th this time around. Those of you who are longtime viewers of this video series know that I used to make the claim that I didn't like to talk about big events in the week because everybody else is talking about them, right? So I like to just kind of keep steady on talking about what kind of double stars or galaxies or nebulae or whatever it is you might be able to see that week, and stay away from things like meteor showers or stuff like that. But here we are. It's time for the Perseid meteor shower, and I know that last year, probably the last 2 years, we've talked about the Perseid meteor shower, the Geminids when they've come around. So I'll let you decide whether that means that I've just decided to give the people what they want to hear, actually, or whether I've just given up and it's the easy way out. I don't know. But maybe we'll talk about the Perseid meteor shower in a little bit different way than other people are talking about it out there. So let's start there and say that, actually, let's start with the planets before we get to the meteor shower. So on the early morning of the 8th, just before sunrise on the 8th, the 50% full moon, the moon is waning away, and the 50% full moon is going to pass right by Jupiter. It's going to be a very beautiful pairing that morning. Jupiter rises into the sky around midnight. So you'll see Jupiter climbing into the sky about midnight. Saturn is about 70 degrees away from Jupiter. And so it rises as it's getting dark. You know, as it's getting dark, Saturn should be crawling over the horizon. And so you'll see Saturn will be well around to the south. That's, 90 degrees. As Jupiter was rising, 90 degrees would be right here, straight south. And so Saturn's going to be very high in the sky by the time Jupiter's climbing into the sky at midnight. So watch the moon, the waning moon, slide by Jupiter, and then pay attention to Saturn as well and enjoy these things. Now, the reason we bring these up, we've talked a fair amount this year about retrograde motion. This is how Copernicus described decided, we were trying to think about heliocentric, whether we're orbiting the sun or whether things are orbiting the Earth. The idea, what really separated these models, was the cause for retrograde motion. The planets normally track east against the background stars, and there's some faint stars in this region, and you can watch Jupiter tracking east. Jupiter's in prograde motion, normal forward motion over the next week or so, or 2 weeks. You can watch Jupiter do this, or longer if you want. Saturn entered retrograde motion a while ago. We talked about it when it did it, and it's very close to a star, a fifth magnitude star, Sigma Aquarii. And so this is a nice close star right there. Fifth magnitude you can see with your naked eye, or you can have a pair of binoculars. It'll be very easy. And you can watch over the course of the week ahead. Saturn is moving the other direction relative to the background stars. Saturn's moving west relative to the background stars. So the opposite direction of what Jupiter's doing. So it is in retrograde motion. Okay? So this idea allows us to think about the sun-centered system. Now, it was Kepler who really built the model of that sun-centered system. And one of the things Kepler did was Kepler suggested that the planets, one of the big step forward for Kepler that really allowed him to model these systems, to model the solar system and understand what the planets were doing, was that the planets weren't moving in circular orbits like previously thought, but elliptical orbits. An ellipse is a squished, that's a technical term, look, it's squished circle, so that the sun is at one focus of the ellipse, and the planet looks, and the orbit looks like this. The sort of how far away the planet gets from the sun compared to how close it gets to the sun, perihelion passage we call that, aphelion out here, how close it gets. That tells you the eccentricity, the ratio of these two things. We won't get into the details of what it actually is, but how much this distance compares to this distance. It gets things with high eccentricity, high squishedness of the ellipse, get closer to the sun and further away from the sun. Things with less eccentricity, close to zero eccentricity, look more like a circle and stay about the same distance away from the sun all the time. Now, the planets have very low eccentricities. They look a lot like circles. It took a lot of really great work by Kepler to figure this out, the data of Tycho Brahe, to figure out what was going on right here, to understand that these were in fact eccentric. Comets have very highly eccentric orbits. So comets are way out here and frozen most of the time. There's these frozen balls of gas and dust and stuff, right? But as they get in here close, they start to boil that stuff off. So they get close enough to the sun to get hot enough to be boiling material away. Now, some of that material is solid. Some of that material is gritty sand and dust and grains. Some of you in school might have had the opportunity to make a model comet where you just dumped dry ice and sand and grit and rocks and stuff in there. And as that gets close, that dry ice sublimates. That dry ice turns into gas, and other stuff turns into gas. Other frozen material turns into gas. And the rocks, the grit, the stuff boil off, and they're pushed away by the sun. So we see the comet's tails, and the comet's tails are pushed away by the sun. Someplace here, I pulled out a picture of a comet to show you, and there it is. I put it right back on the shelf. So there's a comet. That's Comet Hale-Bopp, and you can see, got a lot of reflection in here, but you can see, maybe I can get rid of some of that. The white tail curling back this direction, and the blue tail blowing straight away. The blue tail is the gas that's boiled off, and the white tail is let's try it back out here. Maybe you see it better when I'm further away. I was trying to get too close for you. So you see the white tail curling around and the blue tail blowing straight away. Those are the gases. Now that white tail, that gritty material, falls into orbit. It's heavier, and it curls behind. So it's blown off by the solar wind. You see those tails of the comet, and you think, well, it's just like me running through the room right here. My hair's going to flow out behind me. Yes, play along. My hair's going to flow out behind me from air resistance, but there is no air resistance. So where that's coming from for the comet is the sun, particles from the sun, the solar wind blowing that stuff away. So the blue tail always points straight away. It doesn't trail behind the comet. It points straight away from the sun, wherever it is around there, and the white tail curls back in around here. So that's the gas, and that's the dust. And that dust falls back into orbit around the comet. So what that means is, when a comet orbits the sun, it leaves a tube of dust in its path all the way around here. When we hit that tube of dust, we get a meteor shower. So this is what happens, is the Earth plunges into this tube of material, and we see, as that strikes our atmosphere, we see particles from that comet firing out in all directions as that material, as that dust material burns up in our atmosphere, and we see streaks of comets across here. Now, because they're all entering the atmosphere where we're crossing that tube of dust, we see these things streaking out all from the same point in the sky we call the radiant. And because that radiant is in the constellation Perseus looks something like that, pointed up at the back of Cassiopeia up here, we call these Perseid meteor showers. So we're looking north up here. Now, you don't have to look at the radiant to see these. You can look in any direction in the sky, and if the meteors trace back to that point, they're probably from this interaction. Now, there are random meteors every night, that leftover material from the formation of the solar system, or material that's been, a rock has hit the surface of the moon, or an asteroid, or a planet, and blown material up into space, and we run into that material. And so we see, on a given night, good dark night without much moon, because the moon's fading away, it's waning away, we're not going to have much moon this year for the Perseids. This is one thing that's going to make this a really great year for the Perseids, is very low moon. And so, but on a good dark night when you don't have much moon, you can see a meteor, I don't know, it's every 10 minutes or so, right? You go out and every 10 minutes or so, you're going to see a meteor from this leftover dust, this leftover debris from stuff, the asteroids and formation of the solar system and whatnot. And so these get added onto the top of those random meteors, but those random meteors are coming from all directions in the sky. These are coming from the radiant here. Okay? Now, the thing about this is, this tube is big, and it has density variations throughout it. Some places the dust is thick, some places the dust is thin and sparse, and it takes us a long time to travel through this tube of material that's been boiled off by the comet. So the Perseid meteor shower's actually been going on for a while, just at a low rate, as we're out here in a low density region of the tube of material, the cylinder of material, the debris that was left behind. I think I saw a Perseid meteor a few nights ago. It looked like it was coming from the direction of the radiant above Perseus in the north right up here. It's possible that we hit a random nightly meteor and it looks more or less like it's coming from that direction. So I can't say with 100% certainty, but I saw a very nice meteor just a couple nights ago that looked like it was coming from that direction. So anyway, I think I've already been seeing them, and you could have. If you graph the number you would expect to see as a function of time, it looks something like this, and you have a peak where you hit the densest part of the tube. And forecasters, the people who model these things, suggest we're going to hit a very dense part of the tube this year. So that's the second thing that makes this a really good year to go out and check out the Perseids, is we should hit this dense and get this, and so this is time across here, and this is weeks we're talking about, weeks across here. So you can go out, as soon as you watch this, you can go out and start looking for Perseid meteors. If you have the time and the energy and the fun, go out and do it every night this week. Start on Monday night, Tuesday night, after midnight. So go out after midnight. That's when the radiant's getting highest in the sky, and the moon's getting lower in the sky, and the moon's fading away. It's waning away again as the week goes on, so you won't have to worry about that later in the week. But go out and start counting meteors, and just count meteors each night. Spend an hour outside enjoying the stars, and write down how many meteors you see in an hour each night, and see if this changes over the course of the week. And so this peak right here should be, for observers here in North America, that peak should probably be in the morning of the 13th, after midnight. The closer you can get to sunrise, to dawn on the 13th, the closer we are to that peak, probably. So anytime after midnight, earlier in the night's okay. You're going to see meteors at 10 o'clock at night for sure, on the morning of the 13th. But the morning of the 12th and the morning of the 14th are probably still pretty good right here. So it's real worth getting out and looking at those things. On the morning of the 13th, I wouldn't be surprised if you could see meteors at the rate of, instead of one every 10 minutes or so, from the random meteors, you're seeing one every minute or something like that. So a good 15 minutes of being outside after midnight on the evening of the night of the 12th into the morning of the 13th should produce several meteors for you to see and enjoy, and a few hours out. And these are things, these meteors are big streaks of light across the sky as the material burns up in the atmosphere. So you don't want to be using binoculars, you don't want to be using a telescope, you just want to be lying back and looking up at the sky and watching these things streak around. So this is, and it's warm this time of year for us Northern Hemisphere observers, and so this is a great time to just get a blanket out and lie on the grass and watch meteors cross the sky and trace them back where they come from and count them and think about comets and think about eccentricities of orbits and Kepler, being able to deduce the geometry of the solar system based using Tycho Brahe's data, and thinking about eccentric orbits, non-circular orbits, and the fact that comets have really highly eccentric non-circular orbits. So they get very close to the sun and they boil this material off that allows these showers to happen. So that's what we're shooting for this week. Enjoy the material early in the week, the moon going by Jupiter, and watch Saturn in retrograde motion next to Sigma Aquarii. And then later in the week, particularly the evening, the morning of the 13th, the night of the 12th, but also the night before that and the night after that, be sure to check out the Perseid meteors. Check them out all week if you get a chance. So should be a good week of observing, everybody. Hope you have some clear skies, and thanks for watching as always.